Corporate sustainability marketing often focuses on high-level commitments, but the engineering reality of heavy industry is that a single operational failure can result in immediate asset destruction and billions in lost enterprise value. A report highlighting a 5% reduction in global water use provides no insight into the actual risk profile of a capital-intensive project. Without asset-level data, these aggregated totals are financially uninterpretable. In heavy industry, environmental and social metrics serve as lead indicators for the quality of management's operational discipline. We are using the SASB framework to translate physical events, like methane venting or clinker calcination, into the specific data points required for financial modeling. For the extractive sector, ESG data functions as operational telemetry that reveals the true condition of the underlying business. Understanding this risk begins with defining the physical boundary of the industrial asset. This coal operation involves a terraced open pit spanning several square kilometers. Production depends on moving millions of tons of overburden using 300-ton haul trucks. In contrast, cement production relies on stationary, interconnected infrastructure. The core is the rotating kiln, where raw materials chemically transform under constant, extreme heat. While these engineering models differ, their respective physical risks must be standardized to fit the corporate income statement and balance sheet. Accurately pricing financial exposure is impossible without first identifying the distinct physical constraints of each asset class. Industry-specific scoping is the mandatory starting point because the business model determines how every subsequent data point is valued. A coal operation's risk profile shifts based on its product, thermal coal for power or metallurgical coal for steel, and its extraction method, whether it is a surface pit or a deep underground mine. These variables dictate long-term demand visibility, extraction costs per ton, and specific regulatory hurdles. In the construction materials sector, an aggregates operation is defined by localized extraction. Profitability here is driven by proximity to demand centers and the management of a high acreage land footprint. This model relies on local logistics and permit stability. It contrasts with the cement model, where the primary driver is the operational efficiency and fuel mix of high-heat kiln infrastructure. A portfolio dominated by aggregate quarries carries different land use and transport liabilities than a portfolio focused on cement manufacturing. Using a generic cross-industry framework fails to distinguish these asset-level differences, leaving investors unable to identify where primary risks reside. Greenhouse gas metrics provide a clear example. A total Scope 1 emissions figure is only useful if an investor can pinpoint the physical process generating the carbon. In underground coal mines, the primary emissions source is often methane released directly from the coal seams and removed via ventilation systems. This methane represents both a climate policy exposure and a safety hazard. Managing it requires dedicated capital investment in gas drainage and monitoring to prevent underground ignition. Cement production faces a different mechanical constraint, clinker calcination. Inside the kiln, temperatures must exceed 1400 degrees Celsius to initiate the necessary chemical transformation. This diagram splits the kiln's output. One stream is fuel combustion. A larger stream is process emissions, carbon dioxide released by limestone heated into clinker. Lowering the clinker ratio reduces these process emissions, directly lowering the company's per-ton liability under carbon pricing. Investors must understand the physical source of an emission to judge if management's mitigation strategy is technically and economically feasible. While carbon pricing affects the long-term margin, localized friction points determine daily production continuity. A global water consumption figure often obscures the most significant risks. SASB requires companies to disclose the percentage of water withdrawn, specifically in regions with high or extremely high baseline water stress. Operations in these regions face higher competition with local communities and agriculture, increasing the likelihood of permit revocations and drought-related shutdowns. Industrial waste must also be categorized by its consequence. Standard operational waste carries a different risk profile than large-scale physical liabilities. This tailings storage facility is an engineered dam storing liquid mineral waste, creating a permanent downstream consequence zone. SASB requires asset-level data like construction method and latest independent technical review dates. An outdated review at high-consequence facilities indicates a gap in risk governance. Safety performance is a direct measure of site discipline. When calculating incident rates, companies must include contract workers. Because contractors often perform high-risk maintenance and construction, excluding them from the data produces an incomplete view of the actual site risk. We also look for long-latency health risks. In minerals processing, this includes cases of silicosis caused by the inhalation of respirable crystalline silica dust. Localized constraints, water stress, tailings governance, and contractor safety are the primary indicators of potential legal and operational liabilities. These operational data points eventually dictate the shape of future financial statements. This chart displays proven coal reserves overlaid with rising carbon prices. As carbon prices increase, extraction costs rise. When total cost exceeds market price, high-cost seams become economically unviable and must be removed from the reserve base. In the extractive sector, proven reserves are economic quantities that fluctuate based on price forecasts and regulatory assumptions. This leads to the assessment of capital expenditure, or CapEx, strategy. A company's CapEx allocation reveals management's actual strategy, providing a clear comparison against their public sustainability commitments. Capital spent on reducing fatal risks or improving water recycling protects the long-term viability of the asset. Conversely, expanding production in carbon-intensive assets without a mitigation plan increases the risk of those investments becoming stranded. CapEx allocation is the evidence that shows whether management is successfully aligning their physical operations with the changing regulatory and market landscape. We have integrated the physical engineering models, the operational data nodes, and the financial forecasts into a single logical system. The SASB framework focuses on the disclosure of disciplined, comparable truths about how a company manages its most material constraints. High-level narrative statements lack value without quantitative metrics, just as raw numbers require operational context to be useful to an analyst. A professional disclosure clarifies exactly which physical asset drives the metric, what controls manage the risk, and how capital is ultimately allocated. Standardizing this operational telemetry allows extractive companies to provide an auditable account of how they protect their license to operate. By utilizing industry-specific standards, investors obtain a direct view of the risks that actually affect asset value. In capital-intensive industries, operational ESG performance is a primary determinant of the stability and resilience of future cash flows.